welcome to lecture 7 in this course on noise control in mechanical systems, and in this lecture we will study about sound propagation through medium boundaries, this being a very important topic if you are in the field of noise control, especially the passive noise control. So, a quick review of what we studied in the previous lecture. We studied about spherical waves, cylindrical waves, and what are the common spherical sources in mechanical system and the common cylindrical sources in mechanical system, and we solved and found the solution of acoustic wave equation for these sources. And the important takeaway was that from the noise control point of view, the harmonic plane waves, they are more dangerous and they need a priority because the attenuation rate is almost 0 in the ideal situation, whereas if it is a spherical wave, it has the highest rate of attenuation over space, and then comes the cylindrical waves. So, in this lecture now we will see about the important concepts called reflection, transmission and absorption, and then another terminology which is called as the acoustic impedance. Once we have derived some relations, then we will go ahead and see what happens when the sound wave propagates from medium 1 to medium 2, and the first case that we will study is when the wave is incident on a medium boundary at the normal angle. So far the linear acoustic wave equation that we were dealing with and the solutions that we were getting for the different waves, the main assumption is that the wave here is propagating in a homogeneous medium, which means the medium is not changing the bulk acoustic properties, that is beta and rho are not changing over space and time for the volume of fluid that is under consideration. But what happens suddenly, suppose a wave is travelling and there is a new medium that it encounters while it is propagating. So, what will happen, and what do you mean by new medium? A medium, overall you can say in short, it is a medium with a different speed of sound, and then the speed of sound is given by c is equal to under root of beta by rho. So, which means a medium having this different beta and rho. So, what happens? So, it is very similar whatever I will go through, you can imagine the light waves as electromagnetic waves and how they encounter one medium to another medium having different speeds, and refraction takes place. In the same way, when the sound waves they encounter a different medium, the wave gets diffracted. This is the diffraction phenomenon, which constitutes 3 important phenomena, which means incidence, reflection and transmission. So, a part of the wave that is incident, it gets reflected back into the same medium, and then some part of it propagates into the second medium. So, again if you are thinking like a noise control engineer, as soon as you come to know that okay, there is a change in the medium, I see that some wave is reflecting back and only some portion is going to get transmitted back. So, the first thing that comes to your mind is that okay, suppose I have got some machinery and I want to control the noise, let me put some barriers or some different materials in the pathway of propagation, because you are putting some different material in the path of the propagation, then you are sort of installing or you are introducing some different media in its pathways. And when you are installing different medias in the pathways, you would be able to encounter this phenomenon, which means the waves just some part of it reflecting, some part of transmitting, and you can use this phenomenon to your advantage and you can create the kind of acoustics you need for your particular problem or particular space at hand. Okay. So, the nature of reflection and transmission, this is the thing that the noise control engineers want to manipulate to get their desired result. And what does it depend on? It depends on obviously the 2 mediums that it encounters and their properties. It also depends on the type of boundary surface, the incident wavefront and the angle of incidence. But in this particular introductory course, we will stick with the planar boundary and the incident being harmonic plane waves. but whatever I would like to state here that whatever results we derive for harmonic plane waves, it can automatically be used for spherical or cylindrical, because after all spherical waves can be thought of as harmonic waves propagating radially outwards, and the amplitude instead of being constant is a function of constant by r. It is a constant by r. So, if you think of spherical waves as a special type of harmonic plane waves, then whatever relations you are deriving, it will hold true, and similarly it will also hold true for the cylindrical waves. So, the basic terminologies in this is that here a wave is incident on a medium boundary. What do you mean by the medium boundary? Very simple, boundary between medium 1 and 2. Acoustic medium 1 and medium 2. Fine. So, incident wave is the wave that is incident on that boundary. Reflected wave is the one that after incidence gets back into the first medium after its interaction at the boundary, and transmitted wave is the one which after the interaction enters into the different medium or the second medium. Okay. Incident, reflected, transmitted. So, then what should be the pressure reflection coefficient? It should be some relation between the reflected and the incident wave. So, here it is what? It is the ratio of the complex pressure amplitudes of the reflected and the incident wave, or simply PR max by PI max. Because it is the ratio of two complex quantities, and I already told in some of the beginning lectures that although in the life see, the acoustic pressure, if you think about it, is actually a scalar quantity and it is real. But why do we take complex quantities into account? Because it makes some of the derivations and the computations much easier if we deal with these exponential functions, because their differentiation, integration is easier, and we know that the basic wave equation is a partial differential equation. So, we would be doing a lot of integrating and differentiating if suppose we are dealing with a complex system. So, hence we represent it in the complex form, and then when we sort of do the ratio of these complex amplitudes, we end up with a complex quantity. It should have a phase and an amplitude. In the same way, so this is denoted by capital R, the pressure reflection coefficient. We have another quantity, pressure transmission coefficient, denoted by capital T. It is the ratio of, same way, the complex amplitude of transmitted by incident wave. It is denoted by capital T, has an amplitude and phase. Then we have intensity reflection coefficient. Just like the pressure reflection coefficient was a ratio of the respective pressures, intensity is the ratio of that respective time averaged intensities of these two waves. The RMS intensity of the reflected wave and the RMS intensity of the incident wave. Let us derive it in terms of the pressure reflection coefficient. So, we know that IRMS we have already studied in the previous lecture can be written as P max whole square by 2 rho C. So, now this Ri can be written as PR max whole square divided by 2 times of rho 1 C1, because here the incident and the reflected waves, they are both in medium 1. So, it is rho 1 C1, which means the density and the speed of sound of the medium 1. Okay. This is something which I will make clear here, and then this is how it is. This gets cancelled out and ultimately we end up with PR max by PI max whole square. And what is this inside the square? It is already, we have defined it as the pressure reflection coefficient. So, this is the thing we get. So, here rho 1 C1 is what? The density and speed of sound. Again, density I will mention as mass density, because as you go into more higher sciences you have different types of density. So, mass density and speed of sound in medium 1. So, this becomes the relation. Intensity transmission coefficient, again the same way, it is the ratio of the time average intensities of transmitted and the incident wave. It is represented by this tau symbol. Let us derive a relation. So, again using the same format, we have tau is this whole thing. Here transmitted wave is in the medium 2. So, we are dividing the Pt max whole square divided by 2 times of rho 2 C2, and the incident wave is in the medium 1. So, here we have rho 1 C1. So, we club it together, we get rho 1 C1 by rho 2 C2, and Pt max by Pi max whole square is what? It is the square of this, because T is a complex function. So, directly the magnitude square we are doing for the pressure transmission coefficient. Okay. Now, what is absorption coefficient? So, we know that when the wave is incident, so here again I would like to make a distinction. See, when we will study about porous materials further down in this lecture series, we will deal with absorption coefficient, and we will come to know that when the wave is incident, then what happens? If suppose you have medium 1, medium 2, and you have a layer of material in between. So, essentially it is a 3 medium interaction. So, in that 3 medium interaction, what happens? At each boundary you have incidence, reflection, transmission, and in that layer of material that is there in between, some energy gets lost. That becomes the energy that is being absorbed. So, we use the term absorbed, but physically the definition of absorption is what? It means that whenever there is an interaction at a medium boundary, some energy, what is the loss in the reflected energy? Because essentially you just see that suppose this is one layer of material. So, you view it like this, a wave came, hit it like this and came back. So, it is hit and come back, but the hitting wave and the coming back wave, there is some loss in the reflected wave with compared to the incident wave. So, just with this you are just using the reference of medium 1. So, it is going hitting and then there is some loss in the energy while returning back. So, what is that loss as a fraction of the incident energy? That gives you the absorption at the surface. So, then it becomes what is the difference in the intensity of the incident and the reflected wave divided by the incident wave in the relative term. So, if you do this, it is 1 minus IR RMS by II RMS. So, this is what? This is Ri, which is simply mod R whole square. So, this becomes another important relationship. Now, there is one other important terminology which we need to know whenever we are discussing about sound propagation through different media, that is called as the impedance. So, we have already, if you are familiar, if you are a science student, you are familiar with the concepts of electricity, electric current flowing, and then the concept of force and the energy flow, then you would know that in general in these kind of situations, impedance refers to the resistance to the flow of whatever quantity you are measuring. And most of the times, because acoustics is newer than the field of electricity, let me put it that way. So, most of the times we derive various analogies from the field of electricity and put it in the acoustics field. So, in the field of electricity, the resistance of any element is what? It is the resistance to the flow of current through that element, okay? And impedance is in the complex quantity of that resistance. In the same way, impedance in the field of acoustics can be thought of as the resistance to the flow of sound waves. This impedance could be offered by either a medium, it could be offered, so resistance to anything, whatever you are trying to measure. Suppose you just want to know in general this medium, what is the resistance it is offering to the flow of sound waves, or you can measure, you have a particular boundary, what is the resistance it is offering to entering of the sound wave, or some kind of lumped structure you can have, like some kind of this black box device, and the sound wave is incident and then coming outside. So, it is offering some kind of resistance to the flow of sound waves. What is the impedance it is offering? Okay. It is a complex quantity. The real part is called as the acoustic resistance, and the imaginary part of this is called as the acoustic reactance, is denoted by the letter Z. Now, there are various types of impedance, as you would have seen in the definition itself, it could be for anything. So, depending on whose resistance you are trying to measure, you can classify your acoustic impedance in that way. So, first type of impedance is the specific acoustic impedance. So, which you can denote as capital Z S A subscript, or you can simply write it as the characteristic impedance or small z. So, in many books you see that sometimes people are using this term, and in some books you see this one, they are both same. Okay. So, what do you mean by that? It is the ratio of the acoustic pressure at a point divided by the particle speed at that point. Now, remember we are using the term speed here, which means that it is not velocity, it is the magnitude of the velocity. So, pressure itself is scalar, the speed also becomes scalar, we end up with a scalar quantity. Okay. So, ZSA is P by mod V, and we already know that V is this is the relation between pressure and velocity. So, the mod of this should be P by rho naught C. So, P divided by P by rho naught C, if you do, you will come up with this whole thing divided by P, you will come up with ultimately this rho C, rho naught C or rho C, rho naught or rho C, whatever way you want to use it. So, you will come up with this term. So, this is the mass density multiplied by the speed of the sound. Now, you do not see any surface area or anything coming over here. So, this means that this is for any point in space, and it is usually used for to characterize a medium. So, let us say we can, if we just want to compare the medium air and the medium water to find out which is better for sound wave propagation. So, here there is no structure in mind that no, we have got a cylindrical tube of wave and a cylindrical tube of water, or we have this much area of water or this much area of air, no structure in mind, just the medium in general. Then we can use this term to quantify the medium's resistance to the sound wave propagation. But if suppose we have got certain element, so let us say we are having the sound waves are propagating, suddenly they encounter this kind of Helmholtz cavity, some kind of cavity they are encountering, and this also has the medium air, this also has the medium air, both of them are having the same medium, right, air and air, and but this air is enclosed into this kind of a neck shaped, narrow neck shaped enclosed cavity, right. So, now in this suppose you have something like this, you have got a resonating element and the sound waves are incident on that. So, you cannot just use this to quantify the difference, right, because this is this is used to just measure for different media like air versus water versus some kind of steel or some kind of solid structure. So, here both the media are the same. So, how will you, so effectively there is no impedance, that is not the case, right. If some resistance is being offered by this element by the virtue of how the medium is being enclosed or how the medium is structured around. So, we need some new type of impedance just to measure what is the resistance offered by this particular structure combining different media. So, there we use acoustic impedance. What is the definition of it? It is the ratio of the complex acoustic pressure on a medium surface. So, suppose a sound wave is incident here. So, what is the pressure at which it is incident on this particular element? Here this thing is the entire element we are taking into consideration, and this is the surface over which it is being incident, that small neck surface. So, the ratio of the acoustic pressure on the medium surface divided by the complex volume velocity on that surface. So, what is the volume velocity of the waves propagating from that surface? So, P by U, which is the volume velocity. The volume velocity is what? It is the velocity multiplied by the surface area. Here I have considered that the surface area and the velocity incident is normal, and I have directly taken the product. But if it is some complex situation where only a component of the velocity is incident, automatically you will have to take that component of the velocity which is normal to the surface area, because to measure volume velocity you want to see how much volume of air, basically you want to see what is the rate of the volume of air that particular wave is pushing forward. Okay. So, the velocity should be able to push it along that surface area. So, automatically this you have to take the component of your V vector, that is normal to your surface area under consideration. So, once they are aligned, you get P by mod V. If suppose they are both in the same direction, in that case, only when this holds true, that is V, when V is perpendicular to the surface area under consideration, then we will have this relationship P by mod V becomes your small z, which we just discussed, divided by S. So, this is one way to make this capital Z small z by S, that is acoustic impedance equals to characteristic by small by the surface area. Another way to write this is you can simply write Z is equal to small z by S perpendicular. So, suppose this is some structure through which it has to flow, some kind of structure, and the sound wave is incident, let us say along this direction. So, you take the equivalent surface area in the direction of the wave propagation. So, S perpendicular means the surface area where this V becomes perpendicular. So, instead of taking this surface area, you would take something which is like this in this particular tube. Okay. Let me illustrate it slightly better. Suppose you had this as a structure, some kind of structure, okay, and the sound wave is incident on that, but instead of incident normally, it is incident in this particular direction. Okay. So, maybe the surface area, this is let us say the surface area S of this particular element, but the wave is not incident normally. So, what you would do? You would take the S perpendicular, the effective surface area normal to V vector. So, you would take something like this, and this becomes your S perpendicular. So, this way you can represent, and it is used, as I told you, for quantifying the resistance of various elements, pipes, ducts, cavities, etc. Then there is another thing called surface impedance or normal specific acoustic impedance, Zn. What is Zn? It is the average acoustic pressure on a medium surface and the normal component of the particle velocity on that surface. Now, this is the term which is used for quantifying what is the resistance offered by a medium boundary. Okay. So, various medium boundaries of various kind of exposed surfaces, just we want to know what is the impedance because of this exposed surface, we can use this terminology. Okay. So, let us say again let us take the example, we have an air medium and the wave is coming and it is incident on a water medium. Okay. In one way it is incident like this, and this is the water medium, and then there is a case 2 when again we have the air medium and the water medium, and the wave is coming like this and it is incident on a water medium whose boundary might be like this. Again we have the same media, we cannot use just we have in both cases we have got the same set of media. Okay. So, we cannot here differentiate between the two things using just the characteristic impedance, because both the media or the media pair is the same. The difference is in the type of boundary and the exposure, okay, in the incident wave. So, here in that case, to characterize this difference on how it is being exposed, we use this particular normal specific acoustic impedance. So, this is a per unit area kind of quantity. Okay. Then the last type of impedance is the radiation impedance. It is the ratio of the force on a vibrating surface and the resultant particle speed of the sound waves it generates. So, this actually measures what? It measures the efficiency with which a vibrating source is generating or it is creating the sound waves. So, here what happens? Let us take the example of the sphere which is contracting and then which is sort of contracting, expanding like this, and it is creating the spherical waves all around. There could be one wave that is sort of moving back and forth with the same kind of volume velocity, and then there is another wave. Suppose we have two spheres, both of them are pulsating or they are expanding and contracting with the same force. So, the force measured on the surface, because it is the surface is sort of vibrating because of the expansion and contraction, we can represent it as the vibration of the surface. So, here both the surface they are in, so the structure that is vibrating, it is with the same force. So, both the spheres they are sort of pulsating with the same force, but with the one sphere we are getting a much larger amplitude sound waves, whereas with the other sphere we are getting smaller amplitude sound waves. Okay. So, they are not, both are not generating equal amount of sound, which means that inherent to that solid structure which is creating, there is some form of impedance element there itself. So, in that situations, how to quantify this? We use the radiation impedance, which says that how efficiently a vibrating source can create sound waves. So, it would be the ratio of the force acting on that vibrating surface, or the force of the vibrating surface, and the resultant speed of the sound wave it generates, and the speed is directly proportional to the acoustic pressure. Okay. So, if you know this definition, then you can think about, suppose some surface has got a higher radiation impedance, what should that mean? Suppose some structure has got a higher radiation impedance, so what does it mean? Is it more efficient at creating sound waves or less efficient? So, let us see, suppose something has got higher ZR, suppose ZR is high, this means for the same particle speed to create the same kind of waves you need a higher force. Okay. So, that means that surface efficiency of creating sound waves is less. So, the more impedance inherent within it for radiating sound waves, the lesser obviously it is going to generate the sound waves. Okay. So, with all these definitions, let us do one classical phenomenon where a plane wave is incident on a planar boundary. So, we already knew that it depends on the type of boundary as well. So, we will take into account a simple case, plane wave incident on a planar boundary at the normal angle. Okay. So, here how do we represent this? We can represent it, this pressure I, as some kind of Pi max into e to the power j omega t minus k1 x, the plane wave representation, and the reflected wave in the same way, it should also have a certain amplitude, but here the incident wave, if suppose we are taking the boundary at x equals to 0 and this is our positive x direction, then the Pi is moving in the positive x direction and the Pt is also moving in the positive x direction, but this is moving in the other way. So, here this would be a plus sign. Now, this is what, this is Pr max, and we know that R is what? It is Pr max by Pi max. So, Pr max can be written as R times of Pi max. So, that is how we are writing. Now, let us see what is the net acoustic pressure exactly just left side of the, in the limit x tends to O negative. You can talk in this term of mathematics as this, x tends to O negative. So, just left side of the boundary, what is the total acoustic pressure which is present? So, you will you simply sum up, because this is acoustic pressure. So, it is independent of the direction of the wave, it is a scalar quantity, we simply add up the pressure. So, we add up the pressure due to the incident wave at x equals to 0, and we add up the pressure due to the reflected wave at x equals to 0, and when you sum up these two equations, what you get? Pi max into, because its x is 0 here, so this quantity automatically becomes 0. So, you get e to the power j t and 1 plus r. So, from the first two equations. Now, we find out what is the net velocity exactly on the left side, just on the left side, or limit x tends to 0 negative. So, Vi, let us see the form, it would be the pressure of the incidence wave, which is this, divided by rho 1 C1. So, here you see here why I am here, the plus and the minus sign depends on the velocity. So, you find the magnitude and you see which is the velocity of the particle wave. Now, because sound is a longitudinal wave, so overall the medium particles are moving forward like this, it is along the Pi direction, so positive. So, we have a positive P by rho 1 C1, but here the reflected wave is moving backwards. So, because this is our positive direction, right, positive x. So, it is moving backwards or away. So, here the velocity of one is forward, whereas the velocity of the other wave, or the velocity is same as the direction of the wave propagation, is backward. So, here we have a minus sign. The velocity is what? It is a vector quantity. So, we ultimately do not just add them up like pressures, we need to have the sign also sorted out. So, we have sorted out the sign and did the same kind of computations, and what we end up with, suppose we want to find at the boundary, we put x is equal to 0 on both these equations here and here, and we add them up to find out the total velocity. We are directly adding them. Why? Because both the velocities, the direction is the same, and the plus minus takes care of whether it is back forwards or backwards. So, directly we are adding them. So, this is the term we end up with. So, by definition, what is the normal specific acoustic impedance? It is the average pressure divided by the velocity, but here let me quickly tell you, this is the specific acoustic impedance. If suppose the normal component of the velocity was to be the same as the actual velocity, which means that the entire velocity is sort of normal to the surface, then the ZSA would be similar to Zn, because here the normal component is same as the velocity itself. So, the impedance we are calculating, so here in this particular case when it is normal incidence, it is P by V, they are same. So, we simply do P by V at x equals to 0 to find out for this surface what is the impedance, and the equations we have derived, we put them, this cancels out, this cancels out, this comes up, we get 1 plus r by 1 by r divided by rho 1 C1, and this is by definition all same for the medium 2, because it is the medium 2 we are entering. So, this becomes by definition the Z of the medium 2. So, the Z of the medium 2 is this by this into this quantity. Now, we know that rho into C is what? It is the characteristic impedance of that medium. So, here it is rho 1 into C1, so which means it is the characteristic impedance of the first medium Z1, small z1. Okay. So, small z2 by small z1 becomes this quantity. If you solve this equation, you can solve it like the traditional way, or you can use the componendo and dividendo property of the proportions, and you end up with this equation. So, this is very important. The reflection coefficient is Z2 minus Z1 upon Z2 plus Z1. So, we have got first equation for the reflection coefficient in terms of the impedances of the two media. So, in the beginning I told you that the reflection and the transmission depends on the medium properties, and that is the dependence that we have derived just now. And for this one it is, now let us take the format of the PT, which is the acoustic pressure of the transmitted wave. It is this amplitude, and transmitted wave is also travelling in the positive x direction. So, we have a minus sign and then some component K2. So, why we are taking different K's for the two medium? So, see, for the first one, for Pi and Pr we have taken some K, K1, and for the second medium we are taking K2. Why? Because these are two different media. The transmitted wave is in medium 2, right. So, K1 was omega by C1 omega. So, in any interaction I want to clarify here that the frequency remains the same, it is the difference in the speed of sound that changes the K, and K2 is omega by C2, both the mediums, because they are different, they have a different speed of sound. So, hence K1 and K2 are different. So, this is the K2 for the transmitted wave. We apply the continuity of pressure, which means that the pressure present just at the left side of the boundary, because the pressure is same, the pressure is not vanishing at that point. So, the pressure at 0 negative should be same as the pressure at 0 positive. It is not suddenly vanishing from at the point. So, we have already solved for the left side, we equate it to the pressure on the positive side, which is PT. So, the PT at 0 t should be the same as Pi 0 t plus Pr 0 t. Okay. So, let us put them. So, in the respective equations, x equals to 0. So, this is the equation we are getting, okay, and fine. So, when you divide the entire thing by this Pi max, so this by Pi max becomes 1, this becomes the reflection coefficient, and this term here becomes the transmission coefficient. you end up with this important relationship, 1 plus r is equal to t. Now, you already have found r, which is this z2 minus z1 by z2 plus z1. You solve it for t, and this is what your t is. So, the amount of reflection you will get or the amount of transmission you will get then essentially depends upon what is the characteristic impedance of the medium 1 and 2. And here it's only dependent on characteristic impedance because we have fixed the per unit area thing. We have made it that this is the per unit area and we have made the planar boundary. Suppose it was some different kind of structure, then obviously it will depend upon the design of the structure itself. Okay. So, with this I would like to end this lecture and hopefully see you next time for some special cases of this particular interaction.